So, thank you for attending. My name is Stephen Noel. I work at the MITRE Corporation. MITRE is a not-for-profit company that is working in the public interest in a number of areas. We're actually manage a number of federally funded research and development centers. So, all the national laboratories like Los Alamos and Sandia, Lincoln Laboratory, those are all federally funded research and development centers. Just like there's actually 7 that are managed by the MITRE Corporation. And so one of those research centers is a Center for National Security, which is the one that I work in. And so the point is that my expertise is in the area of cybersecurity. So working in cybersecurity, there is lots and lots of information that you have to take into consideration. This is just a small sample of the kinds of things that a security analyst would typically have to keep track of. So for example, you have tools that go out and scan your network and look at the endpoints and look at the vulnerabilities that are known about the systems in your enterprise. You have to do things like look at firewall configurations to make sure that vulnerable systems are not exposed to the outside. Things like an ongoing deluge of intrusion detection events that are generated that you have to be able to respond to. And you'd like to be able to put those into context and know, well, what does it really mean to my enterprise if a given alert actually happens to be true? Is it going against a system that I really need to care about? Is it a system that ultimately could be used as a stepping stone, maybe multiple stepping stones that could get to a critical service in my enterprise? And really, lots of things that you need to take into consideration before taking action, given that there's so much going on and so much to keep track of and so much that's changing all the time. There's also things like people will share intelligence about bad threat actors, what their techniques and practices are. So there's also keeping track of all that security intelligence information. Now, there are tools, so obviously then those things are all coming from different sources, different sensors. A good first step is to put that into something like a so-called SIEM, or a security information and event management system, so that you have everything under one sort of analytic umbrella that you can then do queries and try to make sense of this. That's a good first start, but you're still stuck with having to basically pivot as you're trying to put together all these pieces of potentially related information. You're having to do multiple queries and basically pivot manually through your event management system. So, as one example, there's the the well-known data breach from Target, and if you look at the details of that particular campaign that went over, I think, like a month, there actually were. It wasn't just a smash and grab. It was actually a very sort of methodical, multi-step maneuvering of the adversary through not only Target, but actually started at one of their contractors. So the point is that, and actually one of the, they actually had an alert at a sort of an early stage of this attack, and the security team looked at it and actually decided they felt like it was a false alarm or something that they could ignore for the moment. And so, I think the argument is that if they were able to look at that particular event and maybe look downstream from there and have a bigger picture about what could potentially happen as a result of that one incident, they possibly would have taken it more seriously. There's one quote that I like about this that says that what was really meaningful are the little links between incidents which cause the largest problems. So it's kind of suggestive of, it's not the individual data points, but rather how they're related. And so obviously that kind of suggests a sort of a graph model. So we actually we're trying to leverage that idea for a number of years. I actually started this work in 2001 at George Mason University and have continued it at MITRE. And so what we ended up building through those years at George Mason and continuing today is a way to analyze, put together all these pieces of information into a graph model, and then do analytics and visualization against that. So in particular, this tool that we built, Cauldron, takes an expression for how your network is segmented and how the sort of pieces are fit together, where the firewalls are located, and then it looks at the specific firewall rules on each of the firewall devices, which obviously controls how the endpoints can reach one another, the connectivity at a sort of logical level. But then also looking at known vulnerabilities across the endpoints, and then basically iterating over every possible source destination, looking at how it would get routed through the network, what firewalls it would pass, what the rules are that would allow or disallow that particular source and destination to talk to one another, ultimately pointing out exposed vulnerabilities. So you can think of each one of those sort of source destinations as sort of single movement in potential multiple stepping stones going through your environment. And so that's actually what is depicted here. What the tool does is it maps out all those sort of steps through your network and lets you see things like bottlenecks and actually see how an attacker could get from one place to another throughout your environment. So, that's been documented in a number of papers. We ended up getting to a point of maturity that we had enough IP and a working tool that we, formed a company and started selling units. And just to show you some examples of what that tool could do, one of the things is just to be able to constrain the graph. So if you have a big environment and you have lots of possible avenues that an attacker could take, if you wanted to constrain it to say, well, we're mostly concerned about an attack starting maybe from this part of our network, and we have certain key cyber terrain or crown jewels, things that we really want to protect in our environment. So let's constrain that graph to say, show me everything starting from this part of the network, ending on these critical assets, show me everything in between. And often that would be a considerable subset of the full graph. Another kind of analytic was basically giving you a ranked list of exposed vulnerabilities. So saying that this particular instance, this kind of vulnerability is actually shows out in a lot of places in your enterprise, and it's actually exposed through lots of your, or maybe one firewall rule, but it's exposed to lots of places. So, if you sort of the best bang for your buck would be to go and look at these critical, it's sort of the low-hanging fruit. And so that was another analytic, just giving you a list of most frequently exposed vulnerabilities. A few other ones are looking at your firewall rules and looking, basically pinpointing vulnerable services in your enterprise that are directly vulnerable from the outside. So kind of having this notion of who we are, and everything else in our firewall rule set is the outside. Or even looking at relationships in terms of firewall rules, the sources and destinations. So if you were to take the destination of one rule, if it's the source of another rule, building up a graph of that. So regardless of whether there are actually vulnerabilities on those services at each point, you could postulate that there's zero-day attacks, for example. So that's another analytic, is just looking at the rule-to-rule sets of relationships. And so the point was that, while we ended up building all that stuff in custom code, we actually didn't even have a database, relational or otherwise, as a back end. Everything was in XML, and the point is that we looked at a specific kind of analytic, a specific sort of scope of what we were trying to capture in a model, and the kind of analysis we want to do, and we hard-coded, we built something that solved that perfectly. But when you want to then extend the scope of your inquiry, sort of add different things to the model, like, for example, this only showed you the predictive paths, what someone could do. But then if you wanted to correlate that with intrusion detection events to see actually where an attack actually does happen, and then try to predict where it could go beyond that, you would have to do a lot of, it becomes expensive to be able to change the custom code. So we actually, did a lot of sort of prototyping and wrote papers about lots of other features that we ended up not having the time to be able to sort of break our production code to be able to work. So, in fact, this is showing you the kinds of things that in the big picture you would want to take into consideration, or at least you should. Unfortunately, a lot of times in cybersecurity, the left hand doesn't know what the right hand is doing. But this sort of portrays the idea that you need to know about, what's in your environment, how it's configured, and how that sort of configuration and setup lends itself to a particular security posture that you have, and also understanding or sort of mapping what you know about your environment and what the security posture is to what potential attacks are and what the latest and greatest exploits, et cetera, that you're learning from your threat intel. But there's also this idea that it would be really even better if you could focus on sort of a mission criticality. In other words, you could get even more out of your effort by focusing on what's important to your mission and understanding what IT or cyber assets support those mission functions, and then using that to as a framework or a way to drive security decisions. So again, the idea is that we'd like to be able to have an environment, a data model, a way to query and analyze stuff about everything here. And I say a stack because in some sense you could sort of isolate these into layers where you have relationships within a layer or a part of that stack. But then there's also relationships, dependencies from things in a lower part. Things on the top, upper part depend on things at the lower part of that stack. So this thing that I'm calling SCI Graph is I'm actually principal investigator for a MITRE research project that is coming up on the end of its first year. And we've developed this tool called SCI Graph that, again, sort of taking a fresh step, sort of looking at the lessons learned, what I described about being inflexible, and also being able to leverage some of the newer technologies like graph databases that have emerged since we originally started doing this kind of work. We're able to take a fresh start and build this thing sort of the best way or the right way. And so the idea here is that rather than sort of designing your data model, building code to do all the analysis and decide what your queries are and sort of coding stuff just to that set of requirements, you should instead have a sort of a generic data-driven architecture where you build the system, but then it's really what the data model looks like, what the queries are, what the kind of analysis that you can do is really kind of driven by the data, the way that you populate your data model. And so this really kind of harkens back to what we saw this morning about F's napkin, about what I'm basically calling a property graph. So that property graph sort of formulation is, obviously it's very generic. It can describe all, basically almost any kind of set of relationships. And so the idea is that we're capturing our data model in that very generic form, and then build all the analytics are then based on that generic sort of pattern. And so that gives you the flexibility to extend your data model, to morph the data model, and then similarly morph the analytics, which in our case are graph queries. So we also have done a good bit of work on what do you do with, once you do graph queries. So part of the work is just understanding how to sort of capture your problem domain as a graph. What kind of abstractions, what things do you call nodes, what are their relationships, what are the attributes that you capture. But then also, how do you formulate the queries that solve important analytic problems? And so you kind of have to do that iteratively, and I'll give you some examples about how we do that in the cyber domain. But also we've spent a fair amount of time with visualization. Sort of the idea here is, one option would just be, okay, I understand the kind of pattern that I'm looking for. Let me just hard code a query. Maybe there's a few parameters. I'll just put that into a form in a user interface, let the user fill in key parameters, hit execute, and they get maybe a list of things that fit that particular query. And that's certainly some style that we will support. But there's also a kind of midway point, but that you still want to allow your analysts to do sort of ad hoc, because I think it's safe to say you can't always predict, especially more sophisticated analysts you are going to need to do things that are outside the scope of the kind of canned queries that you've thought about in the lab or whatever. So you ideally want to give some flexibility to the analysts so that they can do some sort of exploratory ad hoc queries to pull the data out that fits the particular situation that they're in. And so again, the idea is that, and I'll explain more about what I mean about the ad hoc queries and some examples of that, but then what do you do with it when it comes back? Because if it's a simple list kind of relationship, then obviously you just put it in a table. But if it's inherently sort of unpredictable graph patterns that are coming back from your queries, then obviously visualization becomes an important component of that, of the user experience. So as one example, this is just in a particular, what we call a tag graph, using that cauldron tool that I described. And you can see how the data model is the fact that you have basically sets of machines that are in like a subnet, and then each subnet contains a set of machines. Each machine has one or more vulnerabilities that could potentially be exploited. Inside one of these subnets, and sort of implicitly, it's fully connected. So any machines within a particular subnet can all reach each other's vulnerabilities. So those parts of the graph are actually fully connected, but there's no reason to portray that since you understand that. But then what is shown explicitly are the edges of this graph are from machines in one subnet to machines in another, showing all the different sort of exposed vulnerabilities. So this is saying that that particular source machine can connect to a particular destination or victim machine that has a certain set of vulnerabilities. So then you could click on one of the edges and get a list about the details for that particular set of vulnerabilities from one machine to another. So the first sort of litmus test or just hello world kind of thing is to see if we can capture that data model in a Neo4j property graph. Then could you get the same kind of result through a Cypher query and then do some visualization against the Cypher query result? And so this is literally that. In this case, you can see that you have basically all the nodes are IP addresses, and so there is this blue kind of relationship that just tells you the subnet that each machine belongs in. And the red are vulnerability exposures going from an attacker machine to a victim machine. So these are going across the subnet boundaries. And so, but again, the idea is flexibility. So, this is actually just as a first cut. I like this result because I was actually pleasantly surprised that to me it more clearly show that there were certain machines that were really bottlenecks or sort of places to look as potential sources of attacks. But then again, the idea is that the particular Cypher query, so part of it was just how to capture that as a graph model, but then also formulating the queries that gave you that particular result. So in this case, let's say you really don't care about things that are happening within each subnet. You only care about things going across those subnet boundaries. So you could basically restrict that or to do another query where you only care about things that are going across. So again, this just gives you the idea that you can sort of iteratively do these ad hoc queries to sort of refine the kind of analytic result that you're looking for. For example, in this case, we kind of were able to reduce some clutter that we had from sort of, rather than looking at the full graph model, looking at just a more focused subset of it. Again, using more specific queries. So here's another example of that. This is actually a much smaller network, but we've added, rather than just looking at machines and their vulnerabilities and the subnets that they fall into, we opened up, remember I talked about that stack, things that we needed to look at. So I've started to add more things to that stack. And there's lots of these acronyms you probably haven't heard of. These are, one that you may have heard about, CVE, Common Vulnerabilities and Exposures, is that's actually an effort that was started by MITRE. It's now taken over by NIST, National Institutes of Standards and Technology. It's a nomenclature, it's a standard system for reporting known vulnerabilities about software. There's other ones like CWE for common weaknesses. So it's basically categorizing vulnerabilities, types of weaknesses that they exploit. CPE platforms, the actual software platforms that the vulnerabilities are exhibited on. CVSS, which is a vulnerability scoring system, so a number that ranks how severe each of the vulnerabilities are. There's other ones, but the point is that even for this tiny network, there's 2 points here. One is just to be able to explore and understand and feel confident that you're able to capture the semantics of your environment as a graph and to be able to do queries and get the analytic result that you need. But this also reminds us that you almost always end up with a very huge sprawling graph. And so again, the strategy, there's different strategies, but the one that I'm going to focus on now is sort of applying specific queries that only look at just little parts of that. Again, we've talked about the idea of not having to pivot so much, but this is actually combining, sort of 10 pivots instead of, in this case, 1 million. But that's, again, better than doing one at a time through writing scripts and things like that. So in this case, you got a snort as an intrusion detection system. You got an intrusion alert, and you'd like to understand how is this kind of related to my environment. And so you can see at the top there's a particular query that is supposed to answer that question. So in this case, what we find, so first of all, we're seeing that this particular event is between a certain source and destination machine. So it's from a certain outside domain name to one of our clients on the inside. And again, that's the alert. And in this case, we have correlated the fact that that particular alert is actually known to be detecting a certain kind of attack pattern. Here, I don't know if you can see in the fine print, it's called KPEC, Common Attack Pattern Enumeration and Classification. It's a standardized taxonomy of attack types. So it's sort of saying that this particular event, we know it to be related to or detects a certain kind of attack, which we've also correlated with a known vulnerability. So that attack type actually works against a known vulnerability that's actually associated with the destination machine of that alert. So put 2 and 2 and 2 together, and you say that, okay, here's an alert, and I actually know that I have the machine that it's targeted against actually has the vulnerability, that particular vulnerability, and then I can look at the KPEC entry and look at more details about, basically intelligence about that particular kind of attack. Again, that's part of the idea of being able, that's another thing that MITRE is engaged in a lot, is trying to lead standardization efforts for things like threat intelligence sharing. Now, let's say that you, at some point later, you get a second alert, and you are not sure. A lot of times, you're getting this stream of alerts all the time, and you're never, without doing a lot of research and investigation, you're never really sure how alerts might be related to one another, or if you were able to say that these alerts, if there was a pattern, a larger pattern at play, possibly in play here, it would be good to know that, and how would I actually do that? So this particular query actually is just taking a particular node of a type alert with a particular ID as a sort of starting point of this pattern, and then a particular second alert. So it's saying, show me all the relationships that fit anywhere with a certain set of relationship types between this event and that event. And so you can see the result here that those two alerts there's actually a chain of known sort of stepping stones, and these are, again, sort of hypothetical because they come from a standardized database of attacks, but at least hypothetically, that chain of events that, you detected something, and then a few steps later, you got another hit, another detection, and it turns out that there is a chain of possible causality between those. And in fact, for two of those, there actually are two of those attacks, you actually have known vulnerabilities that are susceptible to that kind of attack. So again, it's giving you more evidence that this is something that you should really take seriously. So let's just say, for example, you say, okay, I'm really concerned about this particular situation. Let me actually look at the most recent thing that I've detected, and let me try to predict downstream what, knowing about my environment, knowing that this could be where the attacker is now. What are the things that the attacker could do downstream or subsequent to this particular event? So here's another query that's sort of, it's open-ended on one end, so it's starting from a known, a node of a specific node in your graph database, but then a query that says, show me everything downstream. So in this case, it turns out to be downstream is a particular database, which it's not shown in this model, but you could, and I'll show you later, you could then have that, a relationship between that database and some mission critical functions, so that you could even conclude that if this really was an attack and it could get to this part of your environment, then this part of my mission is potentially at risk. Again, if you're saying, okay, I'm really concerned now, what are knowing about my environment, what are some sort of places in my environment where I can kind of get control of the situation? So here's a particular query that says, looking at that particular set of machines, that if I think the attacker's here now and I want to keep them from getting over there, then this particular query says, show me all of the topological or infrastructure paths, like the routing, which firewalls does traffic go through between those two machines. So it gives me points out where in the environment I can go make changes to try to block that. And the similar idea, sort of if you're doing some sort of lessons learned or forensics, just like, looking in the heat of the moment, looking downstream, you could also look sort of backwards and say, well, because a lot of times these intrusion detection systems, other sensors, are only picking up some of the activities. And so you want to go back and look at logs in more detail. And so this particular query says, given that here's where the attacker has reached, what are some different paths that the attacker could have taken to get them to that point. So it just helps me focus within the environment where to look at. Now, so I've been showing examples, and I haven't gone into much detail about the particular queries, but as you go through this stuff, you start to build up a more sophisticated property graph model, lots of nodes of lots of different types and relationships of lots of different types, and these potentially complicated queries. So we thought about that and decided that we could basically design what we're calling a domain-specific language, a SCI Graph domain-specific language that sort of encompasses the scope of our data model and the kinds of queries that we're going to do, even the sort of open-ended queries that I've talked about, but a way to sort of look at the different parts of that model, to make queries about that, and then to be able to join or combine sort of sub-queries into larger arbitrary queries. And so what happens is that if you're familiar with ANTLR, ANTLR, is a framework for defining, basically automating like a parsing operation. So there you define your language, your domain-specific language in this case, as an input, and it's like just a grammar, an ANTLR grammar. And so any instance, any string that's supposed to fit that particular grammar, it's like a parse tree or like a English, parsing, sentence parsing. It's able to understand that particular grammar, input grammar. And then for each elements of that parsed tree, we have code that then knows how to convert that to the corresponding cipher. So the bottom line is that we have a language that's written in specifically for a cyber domain, and that actually hides a lot of the, sort of abstracts away a lot of the details. For example, exploit paths actually involves relationships of 1, 2, 3, 4, 5, 6, 7 different types. And so all that sort of knowledge about how your model is expressed or represented is sort of built into that language. So again, it simplifies and provides that layer of abstraction. So now I'm just going to sort of send you on a whirlwind tour of some other examples of applications that we've done with SCI Graph. And so again, the idea is that for each one of these examples is that you continue to build up your data model, your property graph, and so that ultimately any one of these things could be tied together, and then you can evolve your domain-specific language to be able to support that evolving domain space. So this is actually a screenshot of actual customer dependency graph. They actually had to go out. They actually spent months and months, years and lots and lots of people going out. It actually was dictated that everyone in the enterprise would go and capture what it is that they depend on, and sort of what's the information and network assets that each of the components of their critical missions depend on. We've also looked quite a bit at just looking at packet capture data, for example, trying to detect malicious activity within your network. So one of the lessons learned or feedback that we got from that is that this very large graph could contain more, it becomes too cluttered. And many times you really want, as you're doing sort of walking through sort of a play-by-play of how attacks are unfolding, you want to kind of focus at the particular moment that you sort of have a window in time, and you want to focus at what's currently happening. So as part of the user interface, the visualization, we added this behavior where it sort of highlights the most recent and with that sliding window. Another use case, so I've talked about this for like operational environments. Another use case is actually doing modeling and simulation. So we went through another project where we applied SCI Graph for, we basically captured like a process model, if you're familiar with business process modeling. So a process flow with all the timing and relationships about how a process gets carried out. So we capture not only what the mission process is, but also the cyber attackers, cyber defenders, and all the timing and resources it takes for that. And so SCI Graph becomes a window in sort of the simulation as it unfolds. You can track things in SCI Graph. Another application is, I mentioned KPEC, this taxonomy, but when you go to the KPEC site, it's just a set of web pages, and you have to kind of point and click, and it's very laborious, and to be able to navigate through the KPEC structure, it's hard to really understand kind of the big picture about how, like, you have large categories of different types of attacks, and what are the sort of more refined kinds of attacks within those larger groups. And so we built this sort of a navigation system for KPEC taxonomy. Another one, Bitcoin is activity is a lot of commonality, or a lot of things going on bad in cyber involve Bitcoin transactions. So that's another use case that we've taken a look at. So to summarize, I wanted to sort of argue and give you some lesson learned and some examples of how you need to move from a very static sort of design time implementation to a more generic, sort of more modular, and basically modeling that is, if you say no SQL, the schemaless idea, but then that does shift, with that brings a lot of responsibility then for understanding the problem domain, because your end users don't just have point and click, simple queries to create. So you have to be able to manage that data model and be able to communicate that with the users, and that's part of the user interface and the architecture that we're designing as well. So at this point, I'm going to thank you for your time and open it to questions.
Okay, quick question. In your graph database, how you query the complex queries based on the number of attributes, either on the nodes or on the relationship? Are you using any kind of indexing technologies on top of it?
I will think it's safe to say that the work that we've done so far, so the question is, how do we handle queries based on, say, the number of attributes that nodes may have? And part of what I glossed over in the architecture, you may have noticed about, like a document database like MongoDB. So the idea there is that when you do as part of your ingest, that you sort of have this data lake, or if you think about it as all the nodes have all their attribute stuff. And actually, the idea is that you want to only keep what's really needed for doing really graph-like operations like traversals or clustering or whatever those particular analytics are. But then when you have sort of scalar associated, if you want to call it metadata, we tend to sort of keep that out of the graph database. Hopefully that addresses it. Yeah. Yes?
Two quick questions. Is this real time or is this only forensic?
Currently, it is not real time. We've really been considering it as sort of offline analysis tool. We have looked at streaming. I gave the one slide about analyzing TCP traffic, for example, and that would be an example where you would have a streaming model. We have looked at that, and there are some other related research at MITRE about streaming data models, but for our project, we haven't really done a lot on that.
Yeah, and second, is the ingest like Kafka ingest?
I'm sorry, is the ingest?
Through Kafka? Or? You showed a picture of lots of streams. In
Yeah, you know what? We actually, and I didn't mention this either, we actually tend to rely on Splunk as our sort of intermediary between the raw data and what's ultimately in Neo4j.
Thank you for this, by the way. Are you doing any sort of inferential stuff? Bayesian networks, it's a probabilistic graphical model. Looks like it'd be a nice fit.
Yeah.
You're not doing real time, so I think simulation and things like that would be really interesting.
Yeah.
Love to see that.
That's true. That's a good point. And that's kind of a thread that we sort of pursued sort of back in the day. And we have papers, and I think maybe even a patent about some Bayesian things. We haven't picked up on that thread yet in this work. There is another new project that's starting at MITRE that is using Bayesian idea for, I talked about this thing about capturing the cyber to mission dependencies, and I said that so far it's been a very labor-intensive effort. There's a new MITRE project that's looking at being able to infer that automatically, and that does take a Bayesian approach. Okay, thank you very much.